So new for rigid bodies. This wasn't something that came up in particles. Is a moment, and we say moment, but think of a force about a point. And the definition is the moment about A is equal to rho cross F, which you can think of as rho is defined as the point where the force is applied minus the about point, and then that quantity crossed with the force vector. And a way to sort of systematically calculate it is to set up a force as a row in this pancake table. Pancake, artists, row for marzipan. I don't know, someone pointed out I could have said margarine, but that's water under the bridge now. Yeah.
So for your E and A vectors, why do you call them vectors when the definition is coordinates?
Well, you can always think of coordinates as a vector from the origin to the point. So coordinates and vectors are, you can think of coordinates always as vectors. Okay. So this is the point where the force is applied. I know you already have this, but I'm using psychology to make you repeat it. This is the about point. This row vector is P minus A. This is the force vector. And the moment is equal to rho cross F. So you just go down the line calculating one thing after another. Question?
Yeah. I know this is going to be a definition for dynamics part, but on the moment around A. But another thing that we know is that moment is equal to the area moment of inertia times alpha. Are you sure?
Yeah, that's...
How does that equal into this?
Well, you can think of this as the definition of the moment, and what you're talking about is a law that was found empirically to be true, So mathematically, that's not the same as this. Physics-wise, it is. Somebody noticed that, wow, if you measure these two totally unrelated things, they come out equal. And that's the rotational version of Newton's second law. It's not like you can derive it from this mathematically, you know what I mean? Okay, so let's do 2 example problems, or more. I can only see the next 2 pages. So let's say we have this object, and our coordinate system, the origin is, I'm going to use green for the coordinate system, but it's right in the middle. Let's say that this length is 1 meter. This length is 2 meters. And let's choose our about point to be off the body, where this distance is another 1 meter. You can do that. It doesn't always... So you can calculate moments about points that aren't on the body. It still makes mathematical sense. It might not always make physics sense to do it that way, because calculating the moment of this point usually isn't going to have any significant, you're not going to be able to use it in Newton's laws, but mathematically it makes perfect sense. And let's say that we're applying a force of 20,000 newtons upward to the right side. And we want to know what's the moment m sub a produced by that 20,000 Newton force. Well, using the definition that the moment is equal to rho cross F, the rho vector goes from, so this is the point P. That's where the force is applied. The rho vector goes from A to P, so this is the rho vector. You calculate that vector and take the cross product. Using the table, I think once you get used to this, you'll like it because it just systematizes everything. You know, it takes, it lets you do everything the same exact way. It eliminates, you know, it's like when you're thinking in new ways that you make mistakes. Okay, so pancake, artists, row, for marzipan. My original one was Princeton athletes row for money. No, it wasn't. No, that Princeton athletes row for mommy. It actually was, and which I thought was funny, like imagining these rich, like crew people at Princeton, like I got to do this to please mommy or whatever. But it felt sort of mean-spirited, and I think it was left over from getting rejected from Princeton when I was in high school. So I went with a more sterile one. Okay, so let's fill this in. So in this green coordinate system, what are the coordinates of the point where the force is applied? It's going to be positive 1, and then this whole height is 1, so this is positive 1, negative 0.5. And then this is in the plane, so for now I'm going to include all the z components as 0. Later on, to save time or whatever, we'll just leave them off. But I'll write this as 1, negative 0.5, 0. What are the coordinates of the about point? 2, 0, nope. 2, positive 0.5, 0. Any questions about that? So these first two columns are just coordinates. You're just finding the locations of where the force is applied and the about point in whatever your coordinate system is.
So
The origin is the green origin there.
When we're approaching this kind of problem,
Mhm.
is it better to just put the origin at the about point?
Often that's the easiest way to do it. When we get into stuff with multiple bodies, I keep the origin in the same place, so you can't do that for every problem, you know. But, I mean, actually, I suppose you could. You can't do it in dynamics. So I tend not to do that, but it can sometimes simplify the math a little. It's not a big deal either way, I don't think. Okay, so now to get the row vector, it's just p minus a. So the p vector minus the a vector is negative 1, 0. And you can see just eyeballing it, it makes sense that this red vector is this. Okay. Then the force vector, what are the components of this 20,000 Newton force?
0, 25.
Yep. And then 0. And now the cross product. If you take that cross product, you get zeros for x and y. And for z, you get negative 20,000. So MA produced by that 20,000 Newton force is 0, 0, negative 20,000. And then what are the units for moment? Newton meters, yep. And so anybody who works with any kind of machines for work or whatever, you know, you use torque wrenches that measure the moment that you're applying to a bolt or a nut. That's measured in inch pounds or some version of moment. That's what you're measuring with a torque wrench.
I had a question.
Yeah.
So I guess the first row is for X, right? Second row is
Yes.
for Y.
Yes.
So the third row is for Z.
Yes.
Because the zero is only got 2 dimensions. How come the moment has 3rd dimension?
So that, yeah, the
I mean, how come the first? I know this the right hand rule produce that things.
Yeah.
How come the things? Because you're going up. But if the Z is if you the
Yeah.
right hand rule, it should go the other direction.
Yeah, so I was going to say this on the next page, but I might as well say it here. So here are the things to keep in mind about moments. So notice, a moment is always a vector. And its direction is the axis of rotation according to the right-hand rule. Okay, so for example, if you think of a bolt and a wrench again, if you apply a force like this, that's going to create, you know, it's going to make this move in a circular path going in this direction, right? And the moment is a vector that's parallel to the axis of rotation. So if this is moving in a circle like this, the axis of rotation is like the pin that you would have to put in here for it to rotate around. So the axis of rotation is either going this way or that way.
Yeah.
And then it has to work according to the right-hand rule. So my thumb is going this way when my fingers are following that path. Okay? And so the direction of the moment is out. So let's see. Can I draw this? No, I cannot probably. Okay, there's your thumb. There are your fingers.
Transparent, huh? Fingers.
Transparent fingers, yes. Those are helpful for moments. That's a little more like it. Okay, well, anyways, so the axis of rotation comes out of the page to cause a rotation this way.
Okay. That makes sense. But if you think of the shoulder joint as that, and you're going down, and there's the upward force push your arm to that direction, this case might be work for the school, like school going up, but how did this
For a three-dimensional thing?
Yeah.
Well, every moment produces a rotation about a single axis. It produces, on its own, you can think of it as causing a rotation about, so your shoulders can rotate in all these different planes, right? But say you do this combination motion like this. There's actually, when you apply this moment to your arm, your arm is moving in a plane like this, which actually has a single axis of rotation that's like, how did I draw that? That's this way. Okay? So every moment does have a single axis of rotation, even if the joint allows more rotations than that. And the direction of the moment is always in the direction of that individual axis of rotation. Okay. Let's see.
So moment is a torque, right?
Yes. In engineering, we use the word torque for a specific combination of moments. But yeah, in physics, what you call a torque is a moment. It's the same thing that you learned as a torque in Physics 1. Okay, well, unless anyone has any other specific questions about it, I'm just going to go on, and hopefully we can sort of iron this out as we go through example problems and stuff. I mean, it is a tricky, it's a confusing thing, and it just is going to take practice to make sense out of it. All right, the second thing to notice is in 2 dimensions, moments only have a non-zero z component. Because the circular path that the things are moving in are in the xy plane, the axis can only be parallel to the z-axis. Let's do a 3-dimensional example. Okay, so let's say that there's this big plate that's connected to the wall by hinges. That's not going to come up in this problem. And it's supported by a cable that goes from the center of the plate to a point on the wall. The length of the plate is 2 meters. I guess it's square, so this is also 2 meters. And this height is 1 meter. So let's say that this is the about point, A. And the coordinate system we're going to use has x-axis pointing away from the wall, the y-axis pointing up, and the z-axis this way. does that meet the requirements of a right-handed coordinate system? If it doesn't, we don't want to use it. It does. And probably the best way to know that is I wouldn't want to have to redraw that because it took me a long time. But that's not really a good mathematical explanation. So x crossed with y gives you z. Y crossed with z gives you x. And x crossed with z gives you negative y, because y always has to be the weird one. So given that the tension in the cable is 10,000 newtons, we want to calculate the moment about A produced by the cable. And let's be clear about what body we're talking about. This is the moment produced by the cable on the plate, to the plate. Okay, so we know we're going to set up the pancake table and go through all that. What steps do we have to do before we can start to fill out? Or maybe we should just start filling it out and get to the... Yeah, maybe we should just do that. So let's just write this out. Pancake, artists, row, 4, marzipan, and we'll just think about what we need as we get there. Okay, so where's the force applied? Yeah, right. The force is applied to the plate at the origin, so this is just going to be zeros. Any questions about that? That's just finding coordinates in a coordinate system. You've done that a million times. The only thing weird now is these pictures look a little different than most likely pictures that you've seen before, but that's all. You've done this a million times. What are the coordinates of the about point?
1, 0, -1.
Yep, 1, 0, -1. And that's enough to calculate the row vector. Just subtract these two. So 0 minus 1 is -1, 0, and then +1. And that is saying that this is the row vector. Okay, now what about the force? What do we know about that force? This is the one that's going to be a little more time consuming. Yeah, so we can figure out the coordinates of this point. We know the coordinates of this point are 0. And we have to use that unit vector thing in order to come up with a vector that points in this direction and has a magnitude of 10,000. Okay? This is like the kind of thing that you did a couple problems like this in that vector review. So for the force, let's first figure out a vector that's in the right direction. I'll call that u. A vector in the same direction as the cable force on the plate is the coordinates of this minus the coordinates of this. The coordinate of this point on the wall is -1, +1, +1. The magnitude of that vector, the length of that vector, is you get that way, and that's square root of 3. And now to get the unit vector in that direction, you take each of the components of u and divide it by the length. So that is negative 0.577, positive 0.577, positive 0.577. And now the last thing we have to do is the force vector is equal to 10,000, since that's the magnitude, times that direction vector, the unit vector. And so you get 577, that one's negative, positive 577, oh no, 10,000. So those sevens keep going.
It's 5773.
5773?
0.5.
Okay. That's good enough for me. So I'll put all these 3's in here. 5773. So all of this analysis is how we come up with this force vector. And so enter this as negative 5773, positive 5773, positive 5773. And now, finally, to calculate that moment, we just take the cross product of this and this. And I think you get negative 5773, 0, negative 5773. Okay, so what does that mean? And this is in Newton meters. That means that, so if this is our coordinate system, there's x, y, and z. Our moment vector goes in the negative x direction, some distance. It doesn't go anywhere in the y direction. And then it goes in the negative z direction, the same distance. And so the vector looks something like this. It's pretty hard to draw this stuff usefully in 3D. But once you figure out, so if you know the direction of that vector, that says put your thumb in that direction, and that moment causes a rotation that follows the right-hand rule according to the direction your thumb's in. So this is MA, and it gives the axis that the that the moment causes a rotation about. Any questions about that one?
Questions on force.
Yeah.
The fundamental force
the place where the force was applied was 0, 0, 0. Because that cable is attached to the plate at what we called the origin. The about point was at the point negative 1 x, positive 1 y, positive 1 z.
Yeah, the row vector.
Okay. So this one's negative. Well, actually, I think all the rest is correct because I just read my notes on here.
You got it right. The about goes down one to z.
According to that. Negative 1 is the z component.
Yeah, like this, right? So all this is right, but now that moment has changed.
No.
You hit it right the first time.
What did I have right?
A should be 1, 0, negative 1.
About point is 1, 0, negative 1.
Oh, the about point, right. Thank you. Okay. 1, 0, negative 1, and this should be positive. Thanks.
The one that I was asking was about tension.
Yeah.
So the way that you find the tension would be actual force that you subtract.
Yeah, the way you find the force applied by the cable by you have a beginning point and an end point. You subtract those two to get a vector in the correct direction, and then you take you normalize it. You get a unit vector so that you have something in the correct direction with a magnitude of 1, and then you multiply it by the tension in the cable. Just like some of the later problems in that vector assignment, we're doing this exact thing but in 2 dimensions. So I think if this is a little hazy, just go back and look at those problems again, and you should see the connection. Okay. Yep.
Just have a question about the coordinate system.
Uh-huh.
Is that basically arbitrary how we set that up?
Yeah, that was given in the problem. And if there was no coordinate system given in the problem and you did yours differently, then your numbers would come out different. But the thing that wouldn't be different is, so say you chose a totally different orientation for your coordinate system. All your components would come out different. But then if you drew the vector out like this, you'd get a vector that pointed in the same direction in space. So the vectors mean the same thing, but the components depend on what your coordinate system is. Any other questions about that? All right, so that's what moments are. So what are they useful for? So what are moments good for? And the answer is the rotational version of Newton's second law. In general, it says if you add up all the moments about a point A, that's equal to the mass moment of inertia about A times the angular acceleration vector, as long as either A is fixed or B, A is the object center of mass. Okay, that's the general form, and it's sort of complicated. You have to choose the right about point and whatever. For bodies in equilibrium, it's simplified considerably. The rotational version of Newton's second law says this. Add up all the moments about a point A. It's equal to 0. And notice that in the general case, there were severe restrictions on what was allowed to be the about point. The about point either had to be a point that's a point on the body, a material point on the body that's fixed in space, or it has to be the center of mass of the body. The static case holds for any point A. So that's very much to our benefit in this class. So you can just choose your about point based on what makes the math easiest, or arbitrarily. You don't have to think about it at all. Okay, so here are some things to notice about Newton's laws. Newton's laws for rigid bodies in equilibrium. First, once you choose the about point, for a rigid body, you must calculate moments about that point, that same point, for all the forces on the body. Okay, so rotational Newton's second law says add up the moments produced by all the forces, and they have to add up to 0. Say that there's 5 different forces. You can choose whatever point you want as your about point, but you have to keep it the same for all 5 of those forces. Second, in 2 dimensions, Newton's second law gives 2 equations, and rotational Newton's second law gives 1 equation, and so therefore you get 3 useful equations for each rigid body. In 3D, and the reason the rotational Newton's second law only gives 1 useful equation is because, remember, in moments in 2 dimensions only have a non-zero z component. The other 2 are always, the x and y components of your moments are all zeros. And so the only useful equation is the z component of rotational Newton's second law. In 3D, Newton's second law gives 3 useful equations. Rotational Newton's second law also gives 3 equations. So you get 6 useful equations from Newton's laws for each rigid body. All right. Well, no. Let me do the couples thing first, and then we'll take a break. Any questions about this so far? Yep.
With the rotational second law, number 2 there.
Yeah.
One equation. If you only break that up into like x and y components. I know the one will usually run right to the axis. That means perpendicular, so that'll be 0. But that'll still be there because you're both right.
One will always run.
Instead of doing a cross product, just doing.
Oh, I see.
Finding the
Yes.
one that's perpendicular to your.
Yes, you can do that too. Sure. Yep. I think you'll find most of the time in these kind of problems it'll be easier to do it this way. But yes, you're right. They give the same answer. Yep. And there'll be some parts of this class where it'll be considerably faster to do it that way for every problem. I'll try to point that out when we get there. All right. So now we're going to talk just for a minute about couples. Or sometimes people call it moment of a couple. All right, so moments, we've been talking about them the whole class today, and one thing that's definitely true about moments is they depend on the about point. If you change the about point, you change the moment. So the moment of a force, ma, is equal to the quantity p minus a crossed with f. And there's nothing you can do to, you can fiddle with the algebra there, but there's nothing you can do to get rid of the fact that a is in there. You could multiply it out and you get p cross f minus a cross f. There's not too much more you can do to fiddle with it. You can't get rid of the dependence on a. But there is one useful case where the dependence on a goes away. This is like a mathematical magic trick. And that's called couples. But if you have equal and opposite forces, acting at a distance from one another, the dependence on A goes away. Disappears. Dot, dot, dot for suspense. So let me just show why this is, how it works. Because this idea of a couple, these equal opposite forces acting at a distance, you can imagine, is the definition of a couple. Okay, so here's just some arbitrary object. And here's the about point. And over here, we'll call this point P1. And at P1, we have a force F acting. And then somewhere else, we have a point P2. And at P2, we have a force negative F acting. Okay, so F and negative F are a couple. Darnation! Like that?
Yeah.
It says derivation. Okay. Darnation! Okay, so that's a couple. F1 and, or F and negative F acting at a distance from each other. The moment produced by this couple we just have to add up the moments produced by each of these two. So MA is equal to P1 minus A quantity crossed with F. That's the moment produced by F. Plus P2 minus A crossed with negative F. That's the moment produced by that negative F. And if we multiply this out, we get P1 cross F minus A cross F plus P2 crossed with negative F minus A crossed with negative F. And that's P1 cross F minus A cross F minus P2 cross F plus A cross F. And the only two terms that have a dependence on A cancel each other out. You have a positive one and a negative one. And you end up with this moment being equal to P1 minus P2 quantity crossed with F. Doesn't depend on A. So that means that this gives the same value no matter what you choose as your about point. And because of that, you can think of this as just a pure moment. And so in the table, you put it in like this. So pancake, artist, row, 4, marzipan. When you're dealing with a couple, you don't care about any of this stuff. The forces cancel each other because you have one positive and one negative, they cancel. All this stuff is used to calculate is used to calculate, the row vector based on what the about point is. That doesn't matter here. And so you just end up adding this moment m in the last column. So that's what we're going to do with couples. So an example of a physically or intuitively, you can think of a couple as a screwdriver. So if you have a screw, the left half of the screwdriver applies a force F this way. The right half of the screwdriver applies a force F this way. And that produces a pure moment about the screw to turn it. So that's what a couple is doing. It's doing what a screwdriver does. If you can imagine, like when you see a couple appearing in a problem, you can think of it as a screwdriver touching the body at that point and just applying a pure couple to the body at that point. Okay, let's take a 10-minute break. Come back at 2:09, and I'll do an example problem, and then we'll start talking about joints.